Section 3.1, Introduction to Expressions and Equations. This video will help you write algebraic expressions, evaluate algebraic expressions, learn the vocabulary of an algebraic expression, and determine if a number is a solution to an equation. Let's start with some definitions. A variable is a letter of the alphabet that represents an unknown number. An algebraic expression is any combination of variables, operations, and numbers. An algebraic expression must contain at least one variable for it to be an algebraic expression. So now let's take a look at an example that'll kind of help you understand these definitions. So we can describe the number of juice boxes pictured with an algebraic expression. And notice we have a box, a big box here of juices, or juice boxes, and another one. Well, we don't know how many juice boxes are in these boxes, but we know that inside of there's some number of these things. So here's a scenario where we can use a variable to help us describe the situation mathematically. And so this is what we do. This is called our declaration of the variable. And we would say, let B equal the number of juice boxes in each of these cases. We'll call these things cases instead of boxes. So we don't know how many are in there, but we're going to let this variable B represent that number, whatever that is. Once we let B represent this number of juice boxes in a case, then we can write an algebraic expression. And here's our algebraic expression. 2 times B, and remember B is the number of juice boxes in a case, and then plus one more juice box that we have here on the end. So this algebraic expression, even though we don't know how many juice boxes are in each of these cases, will describe that situation mathematically. And what we'll do later on is we'll use this expression then and use some mathematics to solve an equation to find out how many juice boxes are in each of those cases. Now let's take a look at an example that will help you understand how to write a variable expression. So example 1, a college bookstore has 5 boxes of baseball caps and 12 baseball caps on display. And we want to describe the number of baseball caps with an algebraic expression. Well, we have these 5 boxes of baseball caps. So we know that there's some mystery number of baseball caps. So what we can do is say that x is our unknown variable here, and it's going to represent the number of caps in a box. We don't know how many baseball caps there are in this box, but we'll let x represent that amount. Now, once we've declared the variable here, what we can do then is we can describe the situation. So we know that we have 5 of these boxes. Well, that's 5 times x. So in each one of these boxes, there's going to be x amount. And so if we added 5 of those together, we can just simply multiply by 5. Either way, we're going to end up with these 5x's. Plus, we also have 12 caps on display in the bookstore. So we're going to say 5x plus 12. And there is an algebraic expression that will describe the number of baseball caps that the bookstore has. Okay, let's pause your video player now and answer practice question 2. When you're done, hit play to see how you did. Question 2. A college bookstore has 12 boxes of pens and 32 pens on the shelf. Describe the number of pens with a variable expression. Well, the first thing we want to do is decide what our unknown is and declare that with a variable. So let's see. The number of pens is what we're looking for here. So maybe, and you can pick any variable you want to, but I'm going to let P equal the number of pens, because it's not that we don't know how many pens we have, we just don't know how many pens we have in the box. So that's what our unknown is here. So P equals the number of pens in one of these boxes, and we have 12 of these boxes plus 32 pens on the shelf. So I would say, okay, 12 times P will give us the number of pens that we have in these boxes, because I have 12 of those boxes, plus 32 pens on the shelf. So there is our variable expression. Now let's take a look at a definition. Substituting a variable's given value and then finding the value of the entire expression is called evaluating the expression. For example, the variable expression 2b plus 1 that described the number of juice boxes back at the beginning of this section can be evaluated if we know that in each case it contains 30 juice boxes. So here was our expression, 2b, because we had 2 of those boxes, remember, plus one more little juice box there. And we didn't know how many juice boxes we had entirely, but we could describe them with this, 2 times b, and b is the number of boxes, juice boxes in a case, plus 1. Well, we can evaluate this now if we know that there are 30 juice boxes in one of these cases. So what we would do here is we're going to substitute the value of b down here for the variable. Now, one thing when we're substituting a value for a variable, always put parentheses around where the variable was. This will take care of all the mathematics that needs to happen after you make that substitution. So it's a good idea to always put parentheses around there. So where the b was, now I start with a set of parentheses and I put the fact that b is 30. And now you can see the parentheses are telling us there that we need to take 2 times 30. So that's going to be 60 plus 1. And so we have 61, and in this case, juice boxes. Go ahead now and pause your video player and answer practice question 4. When you're done, hit play to see how you did. All right, practice question 4. We're asked to evaluate this expression here, this algebraic expression, 10 minus x, when x is equal to negative 6. Okay, so we'll start by writing an open set of parentheses where the x was. Just come down, write the parentheses. Now I'm going to substitute this value of x equals negative 6. I'm going to plug that in there. You can see now that the parentheses are helping us keep track of these signs. Really what we have here is we kind of have this minus a negative. And remember, anytime we have that double negative, minus a negative, we always kind of turn that into plus a positive. So really what I have here is 10 plus 6, or 16. And now, there's no context here. I don't have to tell you 16 what, because all we were doing here was evaluating the expression. So the answer of 16 is good. Learning the vocabulary of an algebraic expression. So to communicate effectively, it is important to learn the vocabulary of an algebraic expression. When you're talking with your teacher, when you're talking with your classmates, it's important to understand this language so that we have a way to communicate with each other. So we're going to take a look at a bunch of definitions and some examples here to kind of get you familiar with some of these definitions and language that we use when we're doing algebraic expressions or when we're working with algebraic expressions. So let's start with our first definition here. A term can be a number, a variable, or any combination of numbers and variables. So terms pretty covers a lot of different things, and those are kind of the things that make up the algebraic expression. So addition and subtraction signs are the things that separate a term. They separate the term. Let's take a look now at example 5 so you can have a better understanding of what terms in an expression are. So this whole thing right here is called our algebraic expression, remember. Now, inside of this algebraic expression, it's made up of terms. Terms are separated by addition and subtraction, in this case, subtraction. So here's our separation point, here's our separation point. So this has 1, 2, 3 terms. So I'd say, okay, there are 3 terms. List the terms, all right? So the first term is 6y, and that's positive 6y, so I'll go ahead and write that and put a comma. The next term, now one thing we want to do is we always want to carry the sign that's in front of the term. So this next term I'm going to list as negative 4z, and the last term I'm going to list as negative 10. Go ahead and pause your video player now and answer this practice question 6 to help you understand the terms in an expression. Okay, practice question 6. It looks like there's 1, 2, 3, 4 terms there. Let's list them. 15x. You can list this as 1z or just z. Negative 3y, and finally negative 8. Make sure you keep those negative signs on those last 2 terms. Let's take a look at another definition. The terms in an expression are either variable terms or constant terms. Terms that contain a variable are variable terms, and that makes sense. So we got variable terms if it contains a variable, and terms that are constant don't have any variable terms. And you can see why this makes sense here. Here's a variable term, 4x. Now this term can vary because x can take on different values. X can be 1, 2, 3, or any other value we plug in there. So the value of this term can change, and that's why we call it a variable or varying term. A constant term doesn't have any variables at all. And here's a good example of a constant term, negative 10. This thing is always going to be negative 10. It's not going to change, and that's why we call it a constant term. Let's take a look now at example 7 to help you understand how to identify variable and constant terms. All right, 7, identify the variable and constant terms. Well, the variable terms are going to be 6y and 4z. The constant term is going to be negative 14. And notice when I take that constant term, I also take the sign, the negative sign with that. Since they were positive over here, I didn't need to write in the signs. Okay, go ahead and answer practice question 8. When you're done, hit play to see how you did. All right, variable terms would have been 15x, negative z, and negative 3y. Our constant term there was just negative 8. Okay, let's look at some more definitions here. So variable terms have two parts. They have both a coefficient and a variable part. So notice the number out front, the coefficient, includes the positive or negative sign, and it is what is multiplying this variable part here. So we're taking negative 5 times this variable part. A constant term, on the other hand, only has one part. It only has a coefficient. So remember, constant terms don't have any variables, so there's no variable part here, so all we have is a coefficient. Let's take a look at an example that will help you understand how to identify these different parts of a variable expression. Okay, so identify the terms, coefficients, and variable parts. All right, well, let's start with the terms. Here's my first term, 6y squared. That whole thing is the term. My next term is negative xz. My last term is negative 9. Okay, now let's list the coefficients. So for my first variable term, my coefficient is 6. Here it might be hard to see, but it's understood that there is a 1 right there. So my coefficient there is negative 1. And on the last term, my coefficient is negative 9. The first term, my variable part is y squared. My variable part is xz. And on the last one, I don't have a variable part. Go ahead and pause your video player now and answer practice question 10. When you're done, hit play to see how you did. Okay, terms are going to be negative 11, negative xy squared, and negative 7z. The coefficients would be negative 11, negative 1, and negative 7. The variable parts, there's no variable part on that first term. Second one, it's xy squared, and the last one, it's z. All right, we'll look at another definition now. Like terms have variable parts that are exactly the same. And for variable parts to be exactly the same, both the exponents and the variables need to be identical. They need to match identically. Let's take a look at an example here to help you understand this. So we're looking here, and what I'm looking for is variable parts that are exactly the same. So that means same variables, same exponents on those variables. Well, I'm going to start with an easy one here, which is 3 and negative 4. Those are like terms. They don't have any variable part at all, and so that makes them identical. And we've been combining or looking at these like terms for a long time in our life, so I'm going to list those. So 3 and negative 4 are like terms. Notice that negative x cubed and positive 2x could not be listed as like terms because this has an x to the third power, this has an x to the first power. So their variable parts are not identical. So those are not like terms. But we do have like terms right here. Notice 3x squared y and 3yx squared. Even though these aren't in the same order, notice they have the same variable parts. Y to the first power, y to the first power, x to the second power, x to the second power. So those are like terms as well. So 3x squared y and 2yx squared. Remember that multiplication, and that's what we're doing here. This is 2 times y times x times x. The order in which I multiply these things won't make a difference. So all I'm really doing between this one and this one is switching the order here of the x squared and the y. So those are still like terms. Okay, unlike terms, we already talked about. That was the negative x cubed and 2x were unlike terms. Okay, go ahead and pause your video player and answer practice question 12. When you're done, hit play to see how you did. All right, like and unlike terms. So we're looking for identical variable parts here. Let's see. Wow, looks like we got the 6 and the negative 2, so I'm going to go ahead and list those. Those are like terms. Let's see, 7y squared. Is there another one in here with a y squared? Nope, nope, nope. Can't do anything with that. xy. Nope, there's nothing that has a matching part with that. 3x, there's no matching part there, so it looks like we only have one set of like terms, one pair of like terms in there. The rest of these are all unlike terms. So I'd say negative 7y squared, negative xy, 3x, and negative 5xy squared. So those are all unlike terms over there. So go ahead now and pause your video player and answer practice question 13. And this kind of takes everything that we've learned in this section and kind of brings it all together. So if you get all of these right, you got a pretty good handle then on a variable expression and all the parts that make up a variable expression. When you get done doing this, hit play and we'll see how you did. All right, practice question 13. Okay, first we're asked to identify the number of terms. Well, addition and subtraction separates the terms. So this is one term, 2, 3, 4 terms. All right, list any constant terms. So now we're looking for things that don't have any variable parts at all. So it looks like just the 13 there is the constant term. Variable terms, we have negative 5x, we have negative x squared, and we have negative 4x. Be sure that you are listing the signs with these. It's not okay to write 5x here. We want to make sure we have a negative 5x there. Okay. Coefficients, every term has a coefficient. So let's see that. First term has a coefficient of negative 5. Next term, coefficient is 13. Third term, it's understood that there's a 1 there, so that is a negative 1 for the coefficient, and then finally a negative 4 for that last coefficient. Now we want to list any pairs of like terms. Let's see. Get rid of those lines. We're looking for matching variable parts exactly. So it looks like negative 5x and negative 4x are my like terms there. All right, now we're going to shift gears just a little bit now and start talking about equations. And an equation is anything that has an equal sign in it. And that's what we have right here. An equation is a mathematical statement that two expressions are equal. And we've been working with expressions so far. So what we basically have here is an expression on the left, in this case x plus 10, is equal to an expression on the right. In this case, an expression is just 15 on the right. So now if a value is substituted for the variable and it makes this equation x plus 10 equals 15 a true statement, then that value is considered a solution to the equation. And for a simple equation like this, you might just be able to look at that and go, well, 5, because if I have 5 plus 10 is 15, that would be the value for x that would make this a true statement. So that value of 5 would be the solution to that equation. Now let's take a look at an example that's a little more difficult than that last one we looked at, where we could just see what the value was. So now in question 14, we're going to determine if negative 3 is a solution to this equation. Well, what we want to do is we just want to plug negative 3 into this equation. And remember, I said whenever we substitute, we want to put open set of parentheses. So right where that x was, I put an open set of parentheses. Same thing over here. Get those parentheses in. Now I'm going to substitute this. X equals negative 3. We want to know if that works. So I'm going to put negative 3 in here for x, and we'll see if this works. Now I'm just going to go through and simplify each of these two sides. So I'd say, okay, 3 times negative 3 is going to give me negative 9. On the right side, negative 3 plus a negative 4 is going to give me negative 7. Left side, negative 9 plus 2 is negative 7. Then I would say, yes, hooray. Negative 3 is a solution. And so we write that out. If it's asked a question like this formally, we want to make sure we answer that with a statement here. When you're solving an equation and we get down, when we're checking our answers, it's okay to just write check, little check mark like that. And that indicates that yes, it is a solution and it works. Now go ahead and pause your video player now and check to see if any three of these numbers are a solution. So you're going to need to check both 3, negative 4, and negative 5 in this equation and determine if any of those are a solution to this equation. When you're done, hit play to see how you did. All right, let's try the first one. So with the first one, we're going to substitute a positive 3 into here. So let's see, open set of parentheses with a 3. Okay, I'm going to simplify each side. 2 times 3 is 6. On the right side, 3 minus 8, that's going to give me negative 5. 6 minus 4 is 2, so I end up with this statement. 2 equals negative 5. That doesn't work. 3 is not a solution. Okay, so I substituted a negative 4 in, and now I'm going to check to see if it works. So on the left side, 2 times negative 4 is negative 8. Minus 4. On the right side, I have negative 4 minus 8. Another good way to think of this is just negative 4 plus negative 8. That's going to give me negative 12. And then again over here, negative 8 plus negative 4 is going to give me negative 12. So I'm ending up now with a true statement. So then I would say yes, negative 4 is a solution. Notice, it didn't have to be -4 equals -4. It just had to give me a true statement. Okay, and we'll almost never work out that this number and these numbers on the bottom are the same. But as long as this number gives us a true statement, then it is a solution. All right, let's check -5 now. 2 times -5 minus 4 equals -5 minus 8. Let's see. 2 times -5 is -10. -10 plus -4 is -14. On the right side, -5. Now I'm going to think of this as plus -8. So -5 plus -8 is going to give me -13. So it does not work. So I would say no, -5 is not a solution.